Today's lesson is about reciprocals of quadratic functions. We've previously looked at reciprocals of linear functions of the form f at x is equal to 1 over x plus 3, or f at x is equal to 2 over x minus 7. Now what we're doing is, again, focusing on the bottom, we are looking at not reciprocals of linear anymore, but reciprocals of quadratics. And so in the statement up top here, because we're dealing with quadratics, you might be able to factor that quadratic and therefore have 0, 1, or 2x intercepts. And this will give us some more restrictions to deal with and give us some very interesting looking graphs. So let's take a look at the parent function 1 over x squared. What we're going to do in this case is plot this graph using the same features and characteristics as we've done in the past. And it is going to be a quick sketch. So here we go. Looking at the function f at x equals 1 over x squared, let's take a look at restrictions first of all. So when we look at restrictions, we're looking at what values x cannot be. And in this particular case, x cannot be 0. That will make the situation undefined. When that occurs, we are going to have a vertical asymptote at x equals 0. And so we'll state that on our graph. X equals 0 is a vertical asymptote. Then we will look for a horizontal asymptote. And horizontal asymptotes are typically found by substituting in large or small numbers into where x is. And so once again, what happens when x approaches negative infinity? Way to the left. Well, 1 divided by a very large negative number will get very, very close to 0 from the negative side. But because this is a squared, it will always be on the positive. Remember, if you substituted in negative 10 squared, it would be 1 over 100. So as x approaches negative infinity, we would say y approaches 0 from the positive. As x approaches positive infinity, the exact same thing occurs. Y approaches 0 from the positive. And so we end up having another value there. We never really get, or we never do get to 0, so therefore we are going to have a horizontal asymptote at y equals 0. The next step is to take a look at the behavior around the vertical asymptote. So what happens as x approaches 0 from the left? Remember that little symbol meaning from the left. Well, if you were to take a very, very small number, negative, and square it, you would get a very small positive number. 1 divided by a very, very small number is going to be a very large number. So we're going to have a value up here, and the same thing occurs as x approaches 0 from the right-hand side. Y is going to approach positive infinity, and y is going to approach positive infinity. The graph looks something like this. Now, this has a very interesting symbol because many of you have seen this before. This symbol is from the good old-fashioned Atari video game. So that's going to be what we're going to call our reciprocal of our quadratic. We can then go ahead and talk about positive and negative intervals. That would be the next thing to take a look at. When they are talking about positive intervals, they are asking where the graph is above the x-axis or where the y values are greater than 0. And in this particular case, the intervals where the graph is positive is our entire domain except for x equals 0. So I'm going to write this in interval notation, always from left to right. And there are no places where our function is negative. The other thing you might be asked is what is happening with the slope. So where is the slope of the line? Increasing or decreasing? Increasing or decreasing? And we looked at this before in class, and one way to do this is to draw some tangent lines and then make up some values for the slope. So I might say that this line has a slope of +1, this line has a slope of 5, and this line has a slope of 10. Well, 1 to 5 to 10 is going up, so therefore it's increasing. So in the interval from negative infinity to 0, we have an increasing slope. If I repeat the same procedure, finding tangent lines, always moving from left to right, and writing down what I approximate the slope might be. This might be a slope of -10, this might be a slope of -4, and this might be a slope of -1. Well, if you look at these values going from 10 to -4 to -1, the value of the slope is still going up. So as I read from left to right, the slope is still increasing from 0 to positive infinity. So the slope would be increasing. That's a quick overview of our basic parent function, f of x equals 1 over x squared. Let's now take a look at some other interesting functions, and we're going to use the graphing calculator to solve this one. So we would approach this the same way. We'd look at it, we'd identify that the denominator is a quadratic. It could be written out as -2 all over x minus 1 multiplied by x minus 1. But what we want to do is just get a picture of this graph. So we are going to go to the graphing calculator now and let the calculator do our graphing for us. So the function that we have is not going to be 1 over x squared. It's going to be -2 divided by x minus 1 all squared. I'm going to do a zoom 6 and get a picture of this graph. So let's take a look what's happened here. I'm going to change my window settings slightly. I don't need to worry about too high of max, so I'm going to change that to 1. And I notice that it shifted a little bit, but I think that's okay. It gives me a pretty good representation of the graph. So what's happened is the line looks like it's disappeared here, but in fact it's actually hugging this asymptote, y equals 0. It is crossing through a y-intercept that is negative, and if I look over to my equation and I cover up the x value and I solve this equation, I have -2 over 1. So that makes sense. And it looks as though there's a restriction here at 1. And once again, to find our restrictions, what we want to do is we want to take that denominator, in this case it's x minus 1 all squared, and set it equal to 0. Well, to solve this I need to square root both sides, and I'm left with x minus 1 is equal to 0, and when I add 1 to both sides, I do have a vertical asymptote located at x equals 1. So all of those things check out, and we end up with a graph that basically has been reflected over the x-axis, shifted 1 unit to the right, and the little 2 up here actually does something. It's very hard to see, but it does act as a vertical stretch. Let's continue looking at some examples. So here's another question. F of x equals 2 over x squared minus 4. So think for a moment of the parent function. F of x is equal to 1 over x squared. So we have to start thinking about what that 4 does on the bottom. One way to do it is to work through a little technique by identifying. So we're going to identify things like the vertical asymptote, the horizontal asymptote, the x-intercepts, and the y-intercept. And these are characteristics that we need to pull out of each of our functions. So I'm going to pull up a graph once again and start to find out these values. So the first thing we want to do is find our restrictions, which is really a vertical asymptote. So one way to do that is to take the denominator and set it equal to 0. And when we do this, we end up with x is equal to plus or minus 2. Well, here's our first case where we now all of a sudden have more than one vertical asymptote. We have one vertical asymptote at -2 and another one at +2. I'm going to try and get those a little closer so that they look equal distance. The horizontal asymptote can't really be found other than the fact that we've seen in all of the reciprocals so far that there's been a horizontal asymptote at y equals 0. And we're going to talk about why that is in just a moment. So I'm going to label all these before I forget. And now I have all of my vertical and horizontal asymptotes found. Next thing to do is find our x-intercept. And our x-intercept is found by setting y to be 0. So when we set y to be 0 and we go ahead and solve, we multiply both sides by x squared minus 4. Well, 0 times anything is still 0. So we end up with 0 equals 2, which really doesn't make a whole lot of sense. So what we say is that there are no x-intercepts. If there's no x-intercepts, then really what that means is there is a horizontal asymptote at y equals 0. X can never go along, or our function can never touch the x-axis. The last thing to do is our y-intercept, and once again you're just covering up or substituting in a 0, and we can see very quickly that our y-intercept is 2 over -4, which reduces to -1/2. So now what we want to do is we want to plot any of the information that we have. So really the only thing we have is we have a y-intercept at 0, -2. So I am going to plot that 0 and -1/2, labeling all those critical points. That's the only information we have. So now we have to go back to our end behavior. And so I'm going to ask the same question we've asked all along, is what happens as x approaches -infinity? So I'm going to plug in a very large number here. So I'm going to do this over on the side. I'm going to plug in, let's do -10. Nice, a lower number to start. So 2 over -10 squared minus 4 is equal to 2 over 100 minus 4, which is 96. Well, that's a positive number, and it's fairly close to 0. If I were to substitute in -1000 and square it and subtract 4, the 4 really becomes sort of minimal in how it changes the function. But I end up with a value closer to 0. But because it's squared, it has to be above the x-axis. The next thing I could do is I could look at the behavior as it approaches -2. And again, we can take out our calculators and do a couple quick calculations, and that's probably a good idea to do. So let's take a look at what happens when x approaches a value as it approaches -2 from the left. So let's say x is equal to -2.01, and let's try and find where the y value is at that point. So we're going to go back to the calculator for this just to get a little bit more precise answer. And what I'm going to do is I'm going to take 2 divided by -2.01 squared. I'm going to add another bracket in here. And then subtract 4. So when I hit enter, this is going to be the y value, which is at 50, way up here somewhere. And the closer I get to that -2, the larger the y value is. So as x approaches -2 from the left, this is how we'd write it, as x approaches -2 from the left, y seems to be approaching very large positive numbers, or positive infinity. And so we have one section of the graph that looks something like that. I'm going to go over here and repeat the same procedure and take a look at what happens when x approaches positive infinity. And a very similar thing occurs. If I plug in a very large positive number here and square it, subtract 4, it's still positive, but it's approaching 0. So I have another value here. What happens as x approaches negative 2 or positive 2 from the right? What happens as x approaches positive 2 from the right? So that's right in here. Well, if we take those same value, instead of negative 2.01, we plug in positive 2.01, we will get positive 50 once again, just like we had over here. Let's give that the same color. And now we have sort of a mirror image appearing on the right hand side as we do on the left. So there's just a little bit more missing, and here's our last little bit of information. The last little bit of information is we have a y-intercept located at 0 and negative 1/2. Now, I know the rules of asymptotes, I can't cross them. So if I believe that, then as I'm going from my y-intercept and I'm moving towards the left, I either have a choice. I can go up or I can go down. Now if I go up, I have to cross the horizontal asymptote. So that tells me that I have to go down. And the same thing occurs as I move to the right. I can't go up because then I'd be crossing an asymptote, and so I end up moving down. And this is the sketch of a reciprocal of a quadratic of 2 over x squared minus 4. Now, the domain is easy enough to find in this. We can state that just based on restrictions. So it runs from negative infinity to negative 2. It runs from negative 2 to positive 2. And it runs from positive 2 to positive infinity. So 3 separate intervals. The range is a little bit trickier. We can clearly see that the range exists above the x-axis. So it would run from 0, not including 0, but from 0 up to positive infinity. So that's part of it. But the function also exists down here. But it doesn't exist in this area right here, anywhere along here. This whole area, as far as we can go left and right, the function doesn't exist. So there's a little bit of a space here. Well, we're lucky because we know what the y-intercept is in that case, which in turn turns out to be a vertex. And these are symmetrical. So if you're able to find the two vertical asymptotes, then the vertex is located at midpoint, halfway between. So the range in this case is a special one. It runs from negative infinity, which is way down here, all the way up to negative 1/2. And it actually includes negative 1/2, so we need to use a square bracket. And so domain is fairly straightforward. It might be multiple intervals. Range, in these reciprocal of quadratics, you're going to need to find that vertex. This one was nice because it was symmetrical about the x-axis and it turned out to be the y-intercept, but it is not always that. And you do have to be careful.